A conducting disk of conductivity sigma has a radius A and thickness T. If the magnetic field B is applied in a direction perpendicular to the plane of the disk, changes with time at the rate of dV by dt equal to alpha. Calculate the power dissipated in the disk due to the induced current. Okay, so first let's try to find what will be the EMF at any distance. So this is the disk, right? It is having some thickness. So it is having some thickness. This thickness is T. Radius of the disk is A, right? So let's take a ring within the disk. Excuse me. Radius of the ring is R, thickness of the ring is dr. EMF induced in that particular ring is dB by dt, which is 5 times of R square into dB by dt, which is alpha, which is 5 alpha R square. This is the EMF induced, correct? So what will be the current within this tiny ring because of this EMF? It is EMF by resistance of the tiny ring, which is 5 alpha R square by resistance is given by rho L by A or 1 by sigma. Length is 2 pi R. Area of cross section is dr into the thickness, which would make it as 5 alpha R into dr into T into sigma divided by 2 pi. 1 pi also get cancels. It is alpha into sigma into I think we can make it much better by directly calculating the power. We can calculate the power P equals to E square by R, or the tiny power which is dissipated in that tiny ring. E square is 5 square alpha power 4 by resistance is 1 by sigma 2 pi R by dr into T. That is 5 alpha square R cube dr into T by 2 pi. 1 pi gets cancelled out. That's alpha square R cube into T into dr by 2 is T. Integrating on either side. Our piece here, R is going from 0 to A, which is half alpha square R power 4 by 4, limits of integration are 0 to A into T. Right. So only 1 pi is left. There is 1 pi here. Because here we have pi square and pi, so 1 pi is left still. That would make it as pi T alpha square by 8 into A power 4. Pi T. Oh, there is a sigma. Pi T alpha square sigma A power 4 by 8. That would be option A.